This is the third example of propped cantilever beam using consistent deformation method. So the question is, analyze the propped cantilever shown using consistent deformation method and draw shear force diagram, bending moment diagram, and elastic curve. So this is a different type of problem where there is a propped cantilever with an overhang portion. So there is a UDL on the overhang, which is 25 kilonewton per meter over a span of 2.8 meters, and there is a point load here of 25 kilonewtons. The distances are given as 3 meters and 3.2 meters. So let us take the points as A, B, this point is C, and this point is D. This is a problem given, and let us consider that EI is constant. So we have our consistent deformation equation, which is given as deflection due to loads plus deflection due to prop is equal to total settlement. And using moment area theorems, the second theorem of moment area method, we can write deflection as area of BMD divided by flexural rigidity multiplied by centroid resistance. So here we will have to again divide the beam into simpler cantilever beams with loads and with prop. So let us divide this into simpler beams. So one will be cantilever with point load. This is 25 kilonewton per meter, 2.8 meters. This is A, this is B, and this will be 6.2 meters. This point is D, and you have a cantilever with point load. This is 25 kilonewtons. So this is point A, point B, point C, and point D. This is 2.8 meters. This is 3 meters, and this is 3.2 meters. And the other one will be propped cantilever beam with prop. So there is a prop here at point B. Let us take this as reaction at B. So this will be reaction at B, and this distance is 6.2 meters. This is 2.8 meters. Point A, point B, somewhere here is point C, this is point D. Now we will have to draw the bending moment diagrams for these three cantilever beams. So for the cantilever with partial UDL, it will be a hogging bending moment. So the bending moment is like this. So from point A to point B there is UDL, so it will be a curved portion, and the bending moment here will be 25 into 2.8 into half of 2.8, which will be 98 kilonewton meter. And from point B till point D there is no load, so it will be a straight line, and the bending moment here will be 25 into 2.8 multiplied by half of 2.8 plus 6.2. This will be 532 kilonewton meter, and this entire BMD will be negative. And because it is an irregular geometric shape, we will have to divide this into one triangle, one rectangle, and one curved portion. So let me call this point as A, this is B, somewhere here is C, and this distance is D. Now we know this total height is 532 and this total height is 98. So this distance is 98. So the remaining distance will be 532 minus 98, which will be 434. And we know that the distance from B to D is 6.2 meters, and this distance is 2.8 meters. So this will be the bending moment diagram for cantilever beam with partial UDL. And for the second beam, that is cantilever with 25 kilonewton point load, it will be a triangular variation, and the bending moment here will be 25 into 3.2, which is 80 kilonewton meter. This is point A, this is point B, this is point C, this is point D. This distance is 3.2 meters, and this will cause a hogging bending moment, so it is negative. And for the third case, that is for the cantilever beam with prop, it will cause a sagging bending moment. So it will be a triangular variation in this fashion, and the bending moment here will be 6.2 times RB, and this is 6.2 meters. Point A, point B, this is point C, this is point D. This total distance from B to D will be 6.2 meters, and this will be a sagging bending moment. So these are the bending moment diagrams for the cantilever beams. Now the centroidal distance we know should be considered from the centroid till the prop. The prop here is at point B, should be x bar, and for the triangular portion, this will be x bar. For the second beam, this distance will be x bar, and for the third beam, this distance will be x bar. So here what we have to note is anything which is beyond the prop, that is the overhang portion, this is completely neglected. So this is an important point to remember. So this portion is neglected because it lies beyond the prop, right? So these are the centroidal distances. Now using these bending moments, we can calculate area of BMD and centroidal distances and substitute in our consistent deformation equation. So this will be given as, try to write it here. So the first BMD is split into two geometric shapes. One is the rectangular portion and one more is the triangular portion. For the rectangular portion, it is hogging bending moment, and for triangular, it is hogging bending moment. So for rectangular portion, the area of BMD is minus 98 into 6.2. That is the area of BMD divided by EI, and the centroidal distance will be 6.2 divided by 2. And for the triangular portion, it will be minus, area is given as half into base is 6.2 and height is 434 divided by EI, and x bar is 2/3 of 6.2. Then for this triangular bending moment diagram, it will be minus, area of BMD is half into base into height is 80 divided by EI, and the centroidal distance will be 2/3 of 3.2 plus 3 meters. So this will be 2/3 of 3.2 plus 3 meters. And for this triangular portion, it is sagging bending moment. So it is plus, area of BMD is half into 6.2 into height is 6.2 RB divided by EI, and the centroidal distance is 2/3 of 6.2. So this is equated to the total settlement, and in this problem nothing is mentioned about the settlement of supports. None of the supports are sinking or rising, so the total settlement can be taken as 0. So here the only unknown is RB, so we can simplify the whole equation and calculate the value of RB. So if I simplify this equation, I will be getting minus 1883.56 divided by EI minus 5560.99 divided by EI minus 657.07 divided by EI plus 79.44 RB is equal to 0. What I'm doing here is I've simplified each of these equations and have got these values which is equated to 0. So from here, if I simplify this equation, this is divide by EI. So 1 by EI can be sent to the right hand side, which gets multiplied by 0. And the only unknown here is RB. So I will get the value of RB as 102 kilonewtons. This is my R. So now for the given propped cantilever, there is a UDL here, there is a point load here. This is 25 kilonewton per meter, and this is 25 kilonewtons. This is 2.8 meter, 3 meter, and 3.2 meters. Point A, B, C, and D. So here we have calculated this reaction RB as 102 kilonewtons. Because we have a fixed support at point D, there will be a vertical reaction here. So let us call this as reaction at D, which we are supposed to calculate. And for now, let us assume that the direction is upwards. So I can make use of my static equilibrium equation. Sum of all vertical forces is equal to 0. And if I apply this, I will get 102. This is upwards plus RD is equal to 25 2.8 plus this 25. So if I solve this equation, I will get reaction at D as minus 7 kilonewtons. So you see here, we have calculated reaction at D and we have got with a negative value. It means the direction which we have assumed here should be in the opposite direction. So this will be acting downwards and the value is 7 kilonewtons, right? So once you know the reactions, you can draw the shear force diagram. Now let us calculate bending moments at various points. There is calculation of bending moments, and the sign convention used is sagging moments are positive. So I know A is a free end, so bending moment at A will be 0 and bending moment at B will be calculated by considering left hand side. So this will be 25 into 2.8, which is a hogging moment. So it will be minus 25 into 2.8 into half of 2.8, which will be minus 98 kilonewton meter. And bending moment at C, again by considering left hand side, so this will be 25 kilonewton per meter, which is causing a hogging BMD, hogging bending moment. So this will be minus 25 into 2.8 into 2.8 by 2 plus 3 meters. So this is due to the UDL, and I have 102 kilonewtons here, which is causing a sagging bending moment. So this will be plus 102 into 3. That is at point B. So this comes up to minus 2 kilonewton meter. And bending moment at point D, if I consider left hand side, will be due to UDL, this is going to be a hogging bending moment. So this will be minus 25 into 2.8 multiplied by 2.8 by 2 plus 2 meters plus 3.2, that is 6.2, and 102 into 6.2, which is a sagging bending moment. So this will be plus 102 into 6.2 and 25 into 3.2. This is a hogging bending moment. So it will be minus 25 into 3.2. So if I simplify this, it will come up to 20.4 kilonewton meter. So now I've calculated bending moments at various points, so I can draw my bending moment diagram. So first, let us draw shear force diagrams in kilonewtons. That is, from left to right, upward forces are positive, downward forces are negative. So this is my reference line. So from point A to B, there is a UDL which is acting downwards. So it will be minus 25 into 2.8. So this will be inclined, which comes up to minus 70. And here I have upward 102. So minus 70 plus 102 comes to 32. And from point B to C, there is no load. So this will be uniform. And at point C, there is a downward 25. So 32 minus 25 will give 7. And from point C to D, there is no load. So this will be a straight line. And at point D, there is downward 7. So this becomes 0. So the upper region is positive, the downward region is negative. This is the shear force diagram. And bending moment diagram can be drawn in kilonewton meters. This is your reference. So moment at A is 0, moment at B is minus 98. Okay, I think this will be, is it 98 or 9.8? It's minus 25 into 2.8 into Yeah, it is 98. So there is 98 here, and bending moment at C is -2. So somewhere here, this is -2. And bending moment at D is positive 20.4. So somewhere here, this is 20.4. So now, from A to B, it is UDL. So this will be a parabola, be a curved portion. And from B to C, it will be a straight line. And from C to D, this will be a straight line. So this is point A, this is point B, this is point C, and this is point D. And the point where bending moment is 0 is called point of contraflexure. So you can consider this distance as X, and you can use similar triangles because this is a triangular region. This is a triangular region. So this distance will be 3.2 minus X. So if I take similar triangles, that is 20.4 divided by X is equal to 2 divided by 3.2 minus X. So this will give me the value of X as 2.9 meters. That is from point. This is the location of point of contraflexion, and the BMD here is negative and this is positive. And the last one is to draw the elastic curve. So you have your propped cantilever. This is point A, point B, point C, point D. So from point A to B, it is hogging. Point B to point of contraflexure, it is hogging, and from point of contraflexure to point D, it is sagging. So from this point till the point of contraflexure, this entire region is hogging. So your beam has to hog till here, and from point of contraflexure till point D, it sags. So it has to sag like this. This is the point of contraflexure. This is your elastic curve. So this is an important problem because there is an overhang portion beyond the prop which is usually ignored. So this has to be remembered. This is very important. Right, so I'll be solving some more examples on propped cantilever beams using consistent deformation method. Keep following.